Hidden in the Magellanic Cloud lies LMC X-1, one of the most powerful black holes ever found. It bends light, swallows matter, and challenges everything we know about gravity. But how does it work, and why is it so unusual? Stay with us as we explore this cosmic enigma. Please like, subscribe, and share, and tell us in the comments if you could see a black hole up close. What would you want to know? First, thank you for watching. Now let's begin. The local group of galaxies forms a loose assembly bound by gravity stretching across millions of light-years of space. At its centre lies the dominant spiral galaxy known as the Milky Way, and beside it another spiral almost as large called Andromeda. Scattered around these two main galaxies are dozens of smaller companions, some spherical, some irregular, each carrying its own population of stars and clouds of gas. One of the most prominent of these companions to the Milky Way is the Large Magellanic Cloud. Seen from the southern hemisphere, it appears to the unaided eye as a pale patch of mist against the dark sky, a smudge of light that puzzled early navigators, but now is recognized as a distinct galaxy in its own right. Measuring about 14,000 light-years across, the Large Magellanic Cloud is far smaller than the Milky Way, which stretches more than 100,000 light-years, yet it is rich in young stars and regions of active stellar birth. It orbits the Milky Way at a distance of about 160,000 light-years, close enough that tidal forces and gravitational interactions shape its structure. The local group is not tightly clustered. Instead, its members are strung across space in a delicate balance, their mutual gravity preventing them from drifting apart while still allowing each system to retain its individuality. The Milky Way and Andromeda pull most of the smaller galaxies into orbits around them. The Large Magellanic Cloud and its neighbour, the Small Magellanic Cloud, are two of the closest such companions. Their proximity means astronomers can study them in much greater detail than most other external galaxies, resolving individual stars and measuring the behaviour of stellar systems within them. This makes the Large Magellanic Cloud a kind of natural laboratory, where processes that govern galaxies across the universe can be examined at higher resolution. From Earth, the Large Magellanic Cloud sits in the southern sky, in the direction of the constellation Dorado. Unlike distant galaxies, which appear only as faint spirals or ellipses through large telescopes, the Large Magellanic Cloud reveals texture even in small instruments. Its bar-like central feature and sprawling arms of gas stand out in images, and deep surveys have mapped the distribution of stars from its dense heart to its diffuse outskirts. Because it's so close, astronomers can measure the brightness and motion of stars within it, with great precision, offering an anchor for cosmic distance scales. Variable stars such as Cepheids, which expand and contract rhythmically, are used to calibrate distance measurements to galaxies far beyond the local group, and the Large Magellanic Cloud serves as one of the most important testing grounds for these methods. The local group as a whole is bound to an even larger structure, a filament of galaxies flowing toward a gravitational concentration known as the Virgo cluster. Yet for the purpose of understanding LMC X-1, the relevant stage is much smaller, the quiet niche that the Large Magellanic Cloud occupies around the Milky Way. This galaxy has its own supply of gas, its own fields of young clusters, and its own histories of stellar deaths that seed it with exotic remnants such as neutron stars and black holes. Being a satellite of the Milky Way, it feels the constant tug of its giant neighbour. Streams of stars and gas are pulled from its edges, creating tenuous bridges between the galaxies. Computer models suggest that the Large Magellanic Cloud has not been in orbit around the Milky Way for all of cosmic time, but may be a recent arrival drawn in from the outskirts of the local group a few billion years ago. Such an infall would explain its distorted shape and the trail of debris that connects it to the small Magellanic Cloud. Within this setting, astronomers identify the Large Magellanic Cloud as a galaxy of ongoing star formation. Its interstellar medium is abundant in hydrogen gas, both in diffuse clouds and in dense molecular complexes where stars condense. The most famous of these is the Tarantula Nebula, a sprawling region of ionized gas many hundreds of light-years across, home to massive stars and clusters, whose combined winds sculpt the surrounding environment. Radiation from these young stars lights up the gas, making it visible in glowing filaments and arcs. Supernovae explosions occur frequently in such regions, enriching the galaxy with heavy elements and creating compact remnants. The presence of these environments makes it unsurprising that the Large Magellanic Cloud hosts several bright X-ray sources, among them one that would eventually be catalogued as LMC X-1. The local group context also defines why such sources can be studied in unusual depth. Black holes in our own galaxy can be obscured by gas and dust in the disk of the Milky Way, making it difficult to trace their surroundings. In contrast, the Large Magellanic Cloud lies outside that plane, giving a relatively clear view. Its orientation allows astronomers to observe regions of active star formation without the same degree of obscuration. The distance is also ideal, close enough to measure fine detail, yet far enough that entire structures can be captured in a single frame of view. In this sense, the galaxy provides both a foreground and a background stage on which LMC X-1 can be placed. Studying the Large Magellanic Cloud in the broader local group reveals further connections. The distribution of its dark matter halo, though not directly visible, is inferred from the motions of stars and gas. This unseen component anchors the galaxy against the pull of the Milky Way. As the two galaxies interact, tidal forces may trigger new bursts of star formation within the Large Magellanic Cloud, setting the stage for massive stars to live short, luminous lives and end as black holes. The presence of LMC X-1 is not an isolated event, but part of a chain of stellar evolution, driven by the conditions of its host galaxy. The high density of young massive stars within the Large Magellanic Cloud compared to the Milky Way increases the likelihood of such systems forming and being observed. From the perspective of cosmic geography, then LMC X-1 sits in a galaxy that itself is in motion. The Large Magellanic Cloud circles the Milky Way on a path that may one day lead to merger its stars and black holes, eventually becoming part of the larger galaxy. For now, it remains distinct, offering a window into processes that shape galaxies and the exotic remnants that lie within them. By starting from this wide frame, the local group context makes clear how the environment surrounding the Large Magellanic Cloud supports the creation and observation of one of the brightest black hole binaries known beyond the Milky Way. The Large Magellanic Cloud holds a structure that is neither spiral in the classical sense nor spherical, like many of the dwarf galaxies that accompany the Milky Way. It belongs to the category called dwarf irregular, marked by a loose and asymmetric distribution of stars and gas. This shape is thought to arise from both its own internal dynamics and the gravitational pull exerted by its larger neighbours. Unlike the orderly arms of the Milky Way, the Large Magellanic Cloud displays a central bar stretching across its interior, with streams of stars and patches of star-forming gas scattered around it. This irregularity gives the galaxy its character, but also complicates efforts to map it precisely. Distances to individual stars vary across its disk, and its tilted orientation relative to Earth means that some regions are closer to us than others by several thousand light-years. Yet even with these complexities, the Large Magellanic Cloud has been measured with accuracy greater than most external galaxies, providing astronomers with a detailed picture of its mass motion and internal composition. Surveys across the electromagnetic spectrum reveal the different layers of this galaxy. Radio maps trace the distribution of neutral hydrogen gas, showing large arcs and shells blown out by the energy of supernovae. Infrared observations penetrate dust clouds to uncover stellar nurseries revealing clusters still embedded in their birth material. Optical telescopes highlight the bright hot stars that dominate the younger regions, while ultraviolet imaging isolates the most massive of these stars that emit copious radiation. Together, these observations show that the Large Magellanic Cloud is not a static object, but a system undergoing active evolution, with new stars forming at high rates, and old stars ending their lives in powerful explosions. Such a setting makes it fertile ground for studying compact remnants like neutron stars and black holes, which are born from the collapse of massive stellar cores. The chemical composition of the Large Magellanic Cloud differs from that of the Milky Way. Its metallicity, the proportion of elements heavier than helium, is lower. This means that stars in the Large Magellanic Cloud form with fewer heavy elements compared to stars in our own galaxy. Such conditions are thought to influence how stars evolve and what remnants they leave behind. In particular, stars with lower metallicity lose less mass through stellar winds, enabling them to retain more of their mass until the final stages of their lives. As a result, they can collapse into more massive black holes than would typically form in the Milky Way. This may partly explain why bright black hole binaries like LMC X-1 are found within this neighbouring galaxy. The Large Magellanic Cloud also shows evidence of complex interactions with its companion, the Small Magellanic Cloud. A stream of neutral hydrogen gas called the Magellanic Stream stretches tens of degrees across the southern sky, linking the two galaxies and trailing behind them as they orbit the Milky Way. This feature is believed to be the product of gravitational tides and ram pressure, as the pair move through the halo of the Milky Way. Such interactions stir up gas within the galaxies, compressing clouds and triggering fresh waves of star formation. In the Large Magellanic Cloud, this has led to the creation of giant complexes such as the Tarantula Nebula, where massive clusters containing stars hundreds of times more massive than the Sun light up their surroundings. It is in such regions that the progenitors of black hole systems originate, born in clusters where high stellar density and strong winds shape their fates. The structure of the Large Magellanic Cloud includes extended stellar populations stretching well beyond its main body. Surveys of variable stars and red giant branches reveal halos of stars that encircle the galaxy, evidence of both internal processes and external stripping by the Milky Way. These extended structures show that the Large Magellanic Cloud is not isolated, but in constant exchange with its environment. Stars may be pulled away to form tidal streams, and gas may be siphoned off into the intergalactic medium. At the same time, gas from these interactions may fall back, feeding further cycles of star formation. In this web of flows, the galaxy sustains a high rate of massive star creation, laying the groundwork for systems like LMC X-1 to exist. Astronomers classify the Large Magellanic Cloud as one of the most active star-forming galaxies in the local group. Its rate of forming stars relative to its size surpasses that of the Milky Way. Much of this activity occurs in regions influenced by supernova feedback, where the shock waves of earlier stellar deaths compress surrounding gas and seed it with heavy elements. The result is a layered cycle of creation and destruction. Young clusters form their massive stars, burn brightly, and live briefly, then collapse into compact remnants that may later interact with companions. In a few million years, such processes can turn a newborn massive star into a black hole, and in certain circumstances that black hole becomes part of an X-ray binary. The environment of the Large Magellanic Cloud therefore shapes not only the creation of black holes, but also their visibility to observers on Earth. The galaxy's internal motions further highlight its dynamic state. Measurements of stellar velocities show that the Large Magellanic Cloud rotates through not as smoothly as a spiral galaxy. Its bar dominates the kinematics of the central regions, while the outer stars follow elongated paths shaped by tidal forces. Gas clouds drift along irregular orbits, colliding and merging under the influence of gravity. These interactions create shocks that compress gas and spark new bursts of star formation. At the same time, feedback from stellar winds carves cavities and bubbles into the interstellar medium, producing structures many hundreds of light-years across. Viewed as a whole, the Large Magellanic Cloud resembles a patchwork of zones at different evolutionary stages, with some regions quiet and others ablaze with activity. This irregular structure and high activity level make the Large Magellanic Cloud an essential field for extragalactic astronomy. It bridges the scale between the Milky Way and more distant irregular galaxies that cannot be studied in similar detail. By resolving its stars individually, astronomers can test theories of galaxy formation, star cluster evolution, and compact object creation. The proximity of the Large Magellanic Cloud allows precise parallax measurements for many of its stars, while spectroscopic surveys map their chemical compositions. Together, these observations provide a comprehensive view of how a galaxy, with low metallicity and strong external influences, behaves. For the study of LMC X-1, this background is critical because the black hole system does not exist in isolation, but within the broader canvas of its host galaxy. The Large Magellanic Cloud continues to move through space on a trajectory that will eventually alter both itself and the Milky Way. Simulations suggest that in several billion years it may merge with the Milky Way, contributing its stars, gas and black holes to the larger system. Even before that, its gravitational pull affects the Milky Way's disk, creating subtle ripples observed in stellar motions. These motions confirm that the Large Magellanic Cloud is not just a passive satellite, but a significant mass on its own, with a dark matter halo extending far beyond its visible stars. This halo contributes to the dynamics of the local group, altering the paths of nearby galaxies and streams of stars. All of these factors combine to make the Large Magellanic Cloud one of the most studied external galaxies in astronomy. In this broader structural view, LMC X-1 appears as a point of intense energy against the backdrop of a restless galaxy. Its presence cannot be separated from the environment that surrounds it, for the irregular shape, the gas content, and the star-forming history of the Large Magellanic Cloud have all contributed to the conditions that created the system. As astronomers move from the wide context of the local group to the more focused environment of this dwarf irregular galaxy, the stage is set for a closer look at the regions of gas and dust where systems like LMC X-1 are born. Within the Large Magellanic Cloud, certain areas stand out as centers of ongoing star formation, where dense concentrations of gas and dust condense under gravity to produce clusters of luminous young stars. Among these, the Tarantula Nebula is the most celebrated. Spanning more than 1,000 light-years, it is the largest known stellar nursery in the local group. Observed through telescopes, it appears as a complex web of filaments and knots, sculpted by the radiation and winds of massive stars. This region is bright enough to be visible from Earth without magnification, a sign of its extreme activity. Within its heart lies the star cluster 136, a dense gathering of some of the most massive stars, known each dozens to hundreds of times more massive than the Sun. These giants burn at temperatures exceeding tens of thousands of degrees Celsius, flooding their surroundings with ultraviolet radiation that ionizes hydrogen gas and causes the nebula to glow. The combination of radiation pressure and powerful winds drives shock fronts through the surrounding medium, compressing nearby clouds and triggering secondary bursts of star formation. The Tarantula Nebula is not unique in this galaxy. Across its span, dozens of smaller star-forming regions exist, each with its own population of young stars and clusters. These environments are important because they set the conditions for the creation of high-mass X-ray binaries. When massive stars are born in clusters, they often exist in pairs or groups. As they evolve rapidly over just a few million years, one may reach the end of its life and collapse into a compact object while its companion continues to shine. The close proximity of such stars increases the likelihood of interactions that lead to mass transfer and the emergence of luminous X-ray sources. The richness of the Large Magellanic Cloud in such regions makes it unsurprising that one of its brightest binaries was discovered there. Star-forming regions are mapped not only through visible light, but also through emissions at other wavelengths. Radio observations trace cold molecular gas, revealing where future stars are likely to emerge. Infrared detectors see through the dust that obscures young clusters, identifying protostars still wrapped in their natal cocoons. Ultraviolet and X-ray telescopes register the radiation from the hottest and most energetic stars. By combining these data, astronomers piece together the life cycle of massive stars within the galaxy. From this work, it becomes clear that the environment is dominated by cycles of birth and death, with each generation of stars influencing the next. Supernovae explosions inject energy into the medium-dispersing gas in some areas, while compressing it in others. The constant interplay ensures that star formation continues at a high rate. The lower metallicity of the Large Magellanic Cloud compared to the Milky Way influences the behavior of its young stars. With fewer heavy elements in their atmospheres, massive stars lose less mass through stellar winds. This allows them to remain more massive until the ends of their lives, increasing the likelihood that they collapse into heavier black holes. This factor makes the galaxy an ideal environment for producing luminous black hole binaries. Regions such as the Tarantula Nebula, filled with stars exceeding 20 or 30 times the mass of the Sun, provide a constant supply of potential progenitors. When one of these stars ends its life and collapses into a black hole, the presence of a massive companion star can sustain a bright and enduring X-ray source. The interstellar medium here is sculpted by these processes. Enormous cavities called superbubbles form when multiple supernovae occur within a single cluster, sweeping up surrounding gas into shells that span hundreds of light years. Within these shells, new star formation can occur, seeded by the compression of material at their edges. Such structures are visible in optical and radio surveys of the galaxy, testifying to the scale of the feedback cycle. In this dynamic context, compact objects such as neutron stars and black holes are not rare. What distinguishes the particular system under study is its brightness and persistence qualities that allow it to stand out against the busy background of its host galaxy. Astronomers trace its position to a region not far from some of these active star-forming complexes. Its location aligns with the expectation that such systems arise in environments rich in young, massive stars. Observations show that the binary responsible contains a very massive O-type star consistent with the stellar population found in the Large Magellanic Cloud's active regions. The association between these environments and the presence of bright X-ray binaries underscores the importance of star-forming regions as the birthplaces of systems that later evolve into compact object pairs. The observational study of these regions has been enhanced by instruments operating across multiple wavelengths. The Hubble Space Telescope has imaged clusters in the Tarantula Nebula with exquisite detail, revealing crowded stellar fields and identifying stars that push the theoretical limits of mass. Ground-based observatories in Chile and Australia contribute spectra that reveal chemical abundances and wind velocities. Radio telescopes trace the cold gas reservoirs that will fuel future star formation. Together, these observations establish a detailed record of the conditions that prevail in the Large Magellanic Cloud, making it possible to understand not only the galaxy as a whole, but also the environment that nurtures individual binaries. The link between star-forming regions and X-ray sources is also evident in the distribution of bright emitters across the galaxy. Surveys conducted by space-based observatories such as Chandra and XMM Newton show that these sources cluster in regions associated with recent star formation. This correlation provides strong evidence that such systems arise from the evolution of massive stars formed only a few million years earlier. In this case, its proximity to active regions confirms the pattern. The path from massive star to black hole binary is short on cosmic timescales, and the presence of young stellar populations in the Large Magellanic Cloud ensures that this path is well populated. The importance of the galaxy's star-forming regions extends beyond individual systems. They also serve as laboratories for testing theories of stellar evolution under conditions different from those in the Milky Way. By comparing massive stars here to those in our own galaxy, astronomers refine models of how metallicity affects stellar winds, lifetimes and endpoints. These refinements feed back into understanding of how black holes of various masses are produced. The discovery and study of this particular binary therefore cannot be separated from the broader investigation of how galaxies with different chemical compositions shape the life cycles of their stars. From the perspective of a calm survey, the star-forming regions of the Large Magellanic Cloud are the crucibles in which the seeds of compact binaries are forged. Their dense clusters and abundant gas ensure that massive stars form in great numbers, live briefly, and end in powerful collapses. The remnants of these processes, whether neutron stars or black holes, become part of the population of high-energy sources that mark the galaxy's presence in X-ray light. The system at the heart of this narrative stands as one such case born from the restless activity of these regions and now shining persistently for astronomers on Earth to observe. The recognition of this binary as a distinct object in the sky traces back to the era when astronomers first began to detect cosmic X-rays. In the early decades of the 20th century, no telescope on Earth could observe such high-energy radiation, because the atmosphere blocks it from reaching the ground. Only with the advent of rockets and satellites in the mid-20th century did it become possible to measure X-rays from beyond Earth. The earliest detections in the 1960s revealed that the universe was far more energetic than had been expected, filled with discrete sources that blazed in the X-ray part of the spectrum. As instruments improved, astronomers began to catalogue these sources, identifying them in the Milky Way and in nearby galaxies. In the 1970s, observations of the Large Magellanic Cloud revealed several bright X-ray emitters, among them the object later designated as LMC X-1. The name reflects its position as one of the first such sources catalogued in the galaxy, Large Magellanic Cloud X-ray source number 1. At first, its true nature was uncertain. X-rays can arise from many processes, including hot gas around young stars, remnants of supernovae or compact objects accreting matter from companions. Determining which category applied required sustained observation. Satellites equipped with proportional counters and imaging detectors traced its brightness, showing that it remained consistently luminous over time, unlike the transient flares of some other sources. Its steady emission suggested a continuous process of energy release pointing toward an accreting compact object. In subsequent years, as X-ray astronomy advanced with missions such as Uhuru, Ariel, and Einstein, the source became recognized as one of the brightest persistent X-ray objects in the Large Magellanic Cloud, drawing attention for its stability and intensity. The identification of an optical counterpart was essential. X-ray satellites could pinpoint positions only to within a few arc minutes, leaving several potential stellar candidates within each error circle. Ground-based telescopes searched for unusually bright or peculiar stars coinciding with the X-ray positions. In this case, astronomers eventually identified a massive O-type star as the likely companion. This discovery placed the source in the category of high-mass X-ray binary systems, where a compact object accretes matter from a massive star that is still burning hydrogen in its core. The classification aligned with the environment of the Large Magellanic Cloud, rich in such young and massive stars. As technology advanced, the evidence for a black hole rather than a neutron star grew stronger. Neutron stars reveal their presence through periodic pulsations or thermonuclear bursts, but none were detected from this source. Instead, its spectrum and luminosity fit models of accretion onto a more massive compact object. By measuring the properties of the optical companion and the orbital motion inferred from spectral lines, astronomers could estimate the mass of the unseen accretor. These calculations suggested a value well above the maximum possible mass of a neutron star, confirming that the system harbours a black hole. This made it one of the earliest extragalactic black hole candidates to be firmly identified. The discovery history of the binary illustrates the gradual accumulation of evidence that defines modern astronomy. No single observation was decisive. Rather, the case built up over years of data from multiple instruments. X-ray satellites measured brightness and spectral shape. Optical telescopes tracked the companion star, and theoretical models link the observations to the physics of accretion. Each piece reinforced the conclusion that this is a binary system consisting of a stellar mass black hole and a massive O-type star orbiting each other within the Large Magellanic Cloud. The persistence of its X-ray emission has made it a benchmark object for testing models of accretion. Its luminosity remains high but stable, allowing long-term studies without the complications of sudden outbursts or declines. This behavior sets it apart from many X-ray binaries in the Milky Way, which often show dramatic variability. The constancy of the source means that astronomers can observe it over decades and compare results from different generations of instruments. It also means that the system likely maintains a steady flow of matter from the companion star, a process that shapes both the black hole environment and the future of the binary. Instruments such as Chandra and XMM Newton have provided high-resolution X-ray spectra, revealing features that trace the physical conditions of the accreting gas. These data show the presence of a multicolour disk spectrum characteristic of an optically thick and geometrically thin accretion disk. The measurements support the interpretation of a black hole, accreting at a substantial fraction of its theoretical limit, known as the Eddington luminosity. The consistency of these findings across instruments strengthens the classification as a canonical high-mass black hole binary. Beyond its role as a scientific object, the source has also served as a landmark in the broader history of astronomy. Its discovery confirmed that black holes exist not only in the Milky Way, but also in external galaxies accessible to observation with modern instruments. It demonstrated that binary systems with massive companions could be sustained outside our galaxy and studied with precision. This broadened the scope of black hole research, showing that extragalactic systems could contribute just as much to understanding accretion and stellar evolution as those within our own galaxy. The history of observing the binary also underscores the importance of technological progress. Early detectors could barely distinguish its position, but successive missions refined the coordinate spectra and timing properties. Each new generation of instruments added detail, from the broadband spectra of early missions to the high-resolution grating data of modern observatories. The object itself has remained constant, but our view of it has sharpened with time offering ever more precise tests of theory. Such a progression highlights the interplay between stable cosmic phenomena and evolving human capability to measure them. The designation of this system as one of the brightest persistent X-ray sources in the Large Magellanic Cloud continues to shape its importance. It serves as a calibration point for studies of other fainter binaries, and as a reference against which models of accretion can be compared. Its discovery and continued study illustrate how a single object can act as both a specific case and a general template guiding understanding of an entire class of systems. The early identification of this binary has thus set the stage for decades of observation, anchoring its place in the catalogue of cosmic black holes. From uncertain beginnings as just one of several X-ray spots in a nearby galaxy, it has become a cornerstone of high-energy astrophysics, its steady light marking the presence of a black hole in orbit with a massive star. With this background established, attention can turn to the detailed architecture of the system, where the interaction between companion star and compact object shapes the flow of matter and the radiation that reaches us across 160,000 light-years of space. The binary identity of this system defines its character and luminosity. At its core are two very different objects bound together by gravity, a stellar mass black hole and a massive hot O-type star. These companions orbit each other on a timescale of a few days, their mutual pull shaping the flow of matter between them. The optical component, often called Star 32, is a giant with many times the mass of the Sun, and a radius large enough that it nearly fills the gravitational volume permitted to it within the binary. Its outer layers are unstable, releasing powerful winds that rush outward at thousands of kilometers per second. A portion of this gas does not escape into interstellar space, but is deflected into the gravitational influence of the black hole, beginning the process that powers the system's intense X-ray emission. The orbit is determined from careful study of the companion spectral lines. As the star moves toward and away from Earth, the lines shift due to the Doppler effect, producing a cycle that repeats over the orbital period. From these shifts, astronomers calculate that the period is a little over 4 days, evidence that the two objects are separated by only a few tens of solar radii. At such a short distance, the black hole's gravitational field exerts significant influence on the companion pulling material from its extended atmosphere. Although the black hole itself is invisible, its presence is revealed through these orbital effects. The minimum mass required to explain the motion of the visible star is more than 10 solar masses, a value far exceeding the maximum allowed for a neutron star, thereby confirming that the compact object is indeed a black hole. The O-type star dominates the optical appearance of the binary. It shines with millions of times the luminosity of the Sun and radiates most strongly in the ultraviolet. Its surface temperature reaches tens of thousands of degrees Celsius, and its energy output drives the continuous winds that sustain the accretion process. Radiation pressure is the mechanism behind this outflow, as photons scatter off ions in the stellar atmosphere, imparting momentum that lifts material away. Over the star's short lifetime, these winds remove significant mass, but in the present stage they also guarantee that the black hole receives a steady supply of gas. Unlike systems where matter spills directly through a gravitational funnel, known as Roche lobe overflow. Here the mechanism is wind capture, yet the result is a similarly persistent accretion flow. On human timescales, the orbit appears stable, repeating with predictable regularity. Over millions of years, however, the companion will lose mass, gradually altering the orbital separation. Some of the lost material will be captured by the black hole, increasing its mass incrementally, while the remainder escapes into the surrounding galaxy. These changes will affect the balance of forces and the accretion rate, shifting the system into new states of luminosity and behavior. For now, the balance is steady, and the binary remains one of the most consistent high-mass X-ray sources known. Observations also reveal subtle modulations linked to the orbital cycle. As the star and black hole circle each other, the geometry changes from our point of view. At some phases, the star partly obscures the X-ray, emitting regions producing dips in brightness. At others, X-rays from the disk heat the star's facing hemisphere, creating variations in optical light that follow the cycle. These effects allow astronomers to refine measurements of orbital inclination and system geometry, adding precision to estimates of mass and separation. The interplay of optical and X-ray light thus provides a three-dimensional picture of the binary, even though the compact object remains invisible. The presence of such a massive companion star ensures that the system is short-lived on cosmic timescales. Stars with more than 30 solar masses burn through their fuel quickly, lasting only a few million years before collapsing. In the future, the companion will expand and perhaps overflow its Roche lobe, dramatically increasing the accretion rate. Later, it will undergo core collapse, possibly leaving behind another compact object. If the system survives that stage, the pair may evolve into a binary containing two black holes, destined eventually to merge and release a burst of gravitational waves. For now, the system remains in a more stable state, a massive star feeding its compact partner through a steady wind. The distinction between high-mass and low-mass X-ray binaries is important. In low-mass systems, the donor star is often a sun-like star that transfers material slowly through Roche lobe overflow, creating long-lived but less luminous systems. In high-mass binaries like this one, the companion is enormous, its winds powerful and its lifetime short. These binaries therefore trace recent star formation, appearing primarily in galaxies where massive stars are abundant. The location of this system in the Large Magellanic Cloud reflects this connection, as the galaxy is rich in regions of active stellar birth. The binary is not an isolated phenomenon, but one outcome of the galaxy's vigorous cycle of creation and destruction. The stability of this particular pair makes it an important reference for models of high-mass binaries. By studying the orbital dynamics, wind properties, and luminosity, astronomers gain insight into how such systems evolve. The fact that the black hole has remained persistently luminous for decades indicates that the balance between stellar wind and gravitational capture is well established. This balance ensures a constant flow of matter into the accretion disk, a process that will continue until the companion evolves beyond its current stage. In calm summary, the binary configuration explains the system's remarkable brightness. A massive O-type star hot and wind-driven orbits closely with a stellar-mass black hole unseen, except for the radiation produced by infalling gas. Their dance repeats every few days, feeding an accretion disk that glows in X-rays visible across intergalactic space. The source is a textbook case of a high-mass X-ray binary, providing a steady laboratory for studying how matter flows from star to black hole. Its persistence makes it both a particular object of interest and a representative of a broader class linking stellar evolution to the extreme physics of accretion. The companion star in this binary is one of the most luminous of its kind in the Large Magellanic Cloud. Classified as an O-type giant, it radiates immense amounts of energy across the ultraviolet and visible spectrum. Its surface temperature climbs to tens of thousands of degrees Celsius, a level hot enough to ionize gas and to drive intense stellar winds. These winds stream outward continuously, propelled by the pressure of radiation, scattering off atoms in the star's outer layers. Observations suggest that the outflow reaches speeds above 1,000 kilometers per second and carries away several millionths of the Sun's mass each year. For a star holding more than 30 solar masses, this steady loss is significant, altering its structure over its short lifetime and shaping how it will eventually collapse. Within this binary, the winds also sustain the process of accretion feeding the hidden black hole. The brilliance of the companion makes it an anchor for astronomical study. Its spectrum is dominated by broad hydrogen and helium absorption lines, along with traces of heavier elements. These lines shift rhythmically as the star moves in its orbit, providing precise measurements of velocity. From these shifts, astronomers deduce the mass of both partners, a black hole exceeding 10 solar masses and a donor star with more than 30. Such figures make the system one of the most massive known examples of a high-mass X-ray binary, highlighting the unusual conditions of the Large Magellanic Cloud that allow such heavy remnants to form and persist. The stellar wind, though steady on average, is far from uniform. Embedded within it are clumps of denser gas formed by instabilities in the star's outer atmosphere. As the black hole sweeps through this flow, some clumps are captured while others drift past, producing subtle fluctuations in the accretion rate. Gas that falls within the gravitational sphere of influence cannot escape. It collides, shocks, and loses momentum until it spirals inward. The rest escapes into the wider galaxy, adding its energy and mass to the interstellar medium. The gravitational focusing of these winds ensures that even a small fraction, once captured, can sustain the extraordinary luminosity observed from the binary. The effects of accretion are not one-sided. The X-rays from the inner regions of the disk shine back on the donor star, heating the hemisphere that faces the compact object. This irradiation creates a temperature difference between the near side and the far side of the star, an asymmetry that produces variations in optical brightness as the orbit proceeds. The face turned toward the black hole glows slightly brighter, and this modulation offers further evidence of the intense interaction between the two objects. Models of this heating effect help refine estimates of the system's inclination and orientation, improving the accuracy of mass calculations. The O-type star is still in its hydrogen-burning phase, but its evolution will be rapid. With such great mass, it will remain on the main sequence for only a few million years before expanding and altering its structure. In future stages, its radius may grow to fill the Roche lobe, at which point direct overflow of material could replace wind-fed accretion. That phase would produce far higher accretion rates, brighter emission, and potentially greater instability. For now, the star sustains a steady supply through its winds, maintaining a balance that has lasted for decades of observation. The metallicity of the Large Magellanic Cloud plays a role in these winds. With fewer heavy elements compared to the Milky Way stars here, generate winds that are less efficient at driving mass loss. This allows massive stars to retain more of their initial mass through their lifetimes, leading to heavier black holes at collapse. The donor star in this binary exemplifies this effect. Its mass and its ability to feed a persistent accretion disk reflect the chemical environment of its host galaxy. By comparing such stars across galaxies of different metallicities, astronomers refine models of stellar winds, gaining insight into the history of star formation across cosmic time. Spectral observations also reveal the imprint of the binary interaction on the wind. X-ray irradiation changes the ionization state of gas close to the black hole, altering line strengths and profiles. At certain orbital phases, absorption dips in the X-ray spectrum show clumps of wind passing across the line of sight. At others, lines appear broadened by ionization effects. These observations confirm that the wind is not only a source of material for accretion, but also a dynamic medium sculpted by radiation from the compact object. The donor star's presence is therefore central to every observable aspect of the system. Without its winds, the black hole would remain invisible. Its light dominates the optical view, its motion defines the orbital dynamics, and its mass loss powers the X-ray source. The star is both a partner and a provider, a luminous giant sustaining a hidden companion through the outflow of its atmosphere. Each spectrum light curve and orbital modulation observed from Earth bears the imprint of its influence. In the broader perspective, the study of such a massive star paired with a black hole illuminates the paths of stellar evolution. It shows how massive stars do not always collapse in isolation, but can leave remnants that remain bound in binaries continuing to interact across millions of years. It also shows how feedback from a compact object modifies the life of its companion, changing wind structure and surface heating. This feedback shapes the evolution of both partners and contributes to the ecology of their host galaxy. In calm description, the companion star of this system is not merely a background presence but a defining element. Its enormous mass, high temperature, and powerful winds determine the flow of matter, the brightness of the X-rays, and the long-term fate of the binary. By studying this luminous donor, astronomers glimpse both the current state and the future course of one of the most remarkable stellar partnerships in the local group. The transfer of mass from the luminous donor to its hidden partner follows a pathway shaped by wind capture. Unlike systems where matter streams directly through a gravitational funnel, this binary relies on the steady outflow from the O-type star. Its radiation-driven wind surges outward in all directions, yet proximity ensures that some fraction is caught by the black hole's gravity. Gas that passes near enough is pulled inward, its path bent and its speed altered until it becomes bound to the compact object. What begins as a chaotic high-velocity outflow gradually transforms into a structured inflow, setting the stage for accretion. The interaction zone between wind and compact object is complex. As the black hole moves in its 4-day orbit, it plows through the dense stellar outflow, generating a bow shock where the two flows meet. Behind this, shock gas slows and accumulates, some of it drawn inward toward the disk. Numerical models of such systems show turbulent wakes trailing the compact object regions, where gas collides, compresses, and loses momentum. Within these wakes, streams of material form, channeling matter into the gravitational well. For this binary, the process appears remarkably stable, with enough material continually diverted from the stellar wind to sustain a bright and persistent X-ray source. Gas captured in this way cannot fall directly onto the compact object. Conservation of angular momentum forces it into orbit, creating a flow that spirals inward. Collisions among gas particles dissipate energy, allowing material to lose orbital momentum and drift closer with each circuit. The result is a gradual narrowing spiral, a stream that feeds the accretion disk. Though invisible to direct imaging, its effects are written into the X-ray light curve and spectrum. The very steadiness of the emission testifies to the reliability of this mass transfer channel, as clumps and variations are smoothed into a continuous flow at smaller radii. The mode of mass transfer is confirmed by observation. Systems dominated by Roche lobe overflow often exhibit dramatic variability as unstable disks build up and release matter in bursts. By contrast, this binary's steady wind capture produces a more consistent inflow. Its X-ray brightness remains persistently high, but without the large swings seen in other classes of binaries. This stability allows astronomers to model the accretion physics with unusual clarity, treating it as an almost ideal case of continuous wind-fed accretion. Yet the process is not uniform. The donor's wind is clumpy shaped by instabilities in its radiation-driven layers. These clumps pass near the compact object, sometimes enhancing and sometimes reducing the accretion rate. Observers detect these fluctuations as subtle dips or rises in X-ray output correlated with orbital phase. The black hole's own radiation further modifies the wind. X-rays ionize nearby gas, reducing the efficiency of radiation driving and altering the flow pattern. This feedback loop means that accretion is both sustained by the wind and also actively reshapes it, producing a self-regulating system. The orbital motion creates additional modulation. Every 4 days, the compact object moves behind the donor star from Earth's perspective, and the line of sight passes through thicker regions of the stellar wind. At these times, X-ray brightness dips not because the accretion ceases, but because intervening gas absorbs more of the emitted photons. Careful analysis of these modulations reveals the density structure of the wind and helps refine models of how much matter is captured. By combining orbital timing with spectral changes, astronomers reconstruct the geometry of the mass transfer process in impressive detail. Over long time scales, the exchange of mass and momentum reshapes the binary's evolution. As the donor star loses mass to winds and accretion, its structure changes and the orbit gradually shifts. Some of the expelled material is captured, adding to the black hole's mass, while the rest escapes, carrying away angular momentum. These changes, though subtle from one year to the next, accumulate over millions of years, determining whether the system eventually widens, tightens, or transforms into a different configuration. For now, the balance appears steady, allowing the binary to persist in a luminous state that can be observed for decades. This stable transfer of matter is of broader significance. In galaxies across the universe, high-mass binaries like this one contribute significantly to the total X-ray output. By studying a nearby example in detail, astronomers calibrate models that can be applied to more distant systems. The physics of wind capture disk formation and feedback loops is universal, and the lessons learned here extend to environments far beyond the local group. The inflow of matter also sets the conditions for the accretion disk. The density, velocity, and angular momentum of the stream define the outer boundary of the disk and influence its stability. Variations in the wind propagate inward, sometimes detectable, as delayed fluctuations in X-ray emission. Monitoring these patterns helps connect the properties of the stellar wind to the radiation produced near the black hole. In this way, the pathway of mass transfer forms the essential link between the luminous donor and the hidden accretor, binding their fates through a continuous flow of gas. In calm summary, the binary survives and shines because of this exchange. Matter that begins as a stellar wind launched by radiation from a massive star is captured, channeled, and reshaped into a spiral stream. This stream feeds the disk, which in turn radiates in X-rays visible across intergalactic space. The stability of the system demonstrates how gravitational capture can transform chaotic outflows into a luminous and persistent source, bridging the processes of stellar winds, orbital dynamics, and accretion physics. Once the captured gas becomes bound, it cannot plunge straight into the compact object, but instead settles into a rotating structure known as the accretion disk. Conservation of angular momentum requires this outcome. Material drawn from the stellar wind retains sideways motion that prevents direct infall. Collisions within the inflowing stream redistribute energy, gradually circularizing the orbits and flattening the gas into a disk. This disk extends outward from the innermost stable orbit near the black hole to the region where the inflowing stream first settles. In this system, the disk is the central engine converting gravitational potential energy into radiation across the electromagnetic spectrum. The structure of the disk depends on the balance of forces. Gravity pulls the gas inward, centrifugal force holds it outward, and viscous friction allows angular momentum to be transported from one ring of gas to another. The microscopic source of viscosity is thought to be magnetic turbulence generated by instabilities in the ionized plasma. This turbulence acts as an effective friction, allowing gas to drift inward while transporting angular momentum outward. The efficiency of this process determines the rate of accretion and the luminosity of the disk. For this, binary observations of its persistent brightness confirm that the disk remains stable and efficient over long timescales. Temperature within the disk rises sharply with decreasing radius. The outer edges remain comparatively cool, radiating in optical and ultraviolet light. As gas spirals closer, frictional heating intensifies, and temperatures climb to millions of degrees Celsius. These inner zones radiate in soft X-rays, forming the dominant part of the system's spectrum. The multicolor nature of the disk, with each radius emitting at its own characteristic temperature, produces a smooth curve that matches observations. The continuous rise toward higher energies peaking in X-rays is the signature of a hot, optically thick, geometrically thin accretion disk. The geometry of the disk is another important property. In this system, evidence points to a disk that remains thin and relatively flat rather than puffed up by radiation pressure. Its inclination relative to Earth's line of sight is moderate, allowing a clear view of both thermal emission and the harder photons produced in the inner regions. This geometry also ensures that eclipses by the donor star cause only partial dips in brightness, rather than complete blockages, providing additional data about the relative alignment of the orbit and disk. Energy released in the disk follows a predictable pattern. Gas at each radius loses gravitational potential energy as it moves inward, and this energy is converted into heat and radiation. The efficiency of this process, about 10% of the rest mass energy of the accreted material, is vastly greater than that of nuclear fusion in stars. Even the capture of a small fraction of the donor's wind produces a luminosity millions of times greater than the Sun. This efficiency explains why the system shines so brightly, despite the modest fraction of wind material actually captured. The outer disk plays an important role as a reservoir. Gas that arrives from the stellar wind accumulates in these regions, smoothing fluctuations in the inflow. Variations in density or velocity of the wind are damped as matter spreads into circular orbits. Over time, the gas drifts inward, ensuring a steady supply to the hotter regions. This buffering effect helps explain the stability of the system's brightness. Unlike transients that flare and fade, the binary maintains a persistent glow, sustained by the capacity of its disk to average out the irregularities of the wind. Observationally, the disk reveals itself through its spectrum. X-ray telescopes record the soft thermal component, while ultraviolet and optical instruments detect the cooler outer emission. The shape of the spectrum allows astronomers to estimate the inner radius of the disk and, by extension, the spin of the black hole. A disk extending very close to the horizon implies rapid spin, while a more distant inner edge implies slower rotation. For this system, the data favor a rapidly spinning black hole consistent with its high luminosity and stable emission. Magnetic fields carried into the disk by inflowing gas influence its behavior. These fields can become twisted and amplified, possibly launching weak outflows or contributing to the heating of a corona above the disk. In many black hole systems, jets are associated with such processes, but here strong jets are absent consistent with the soft state. Still, the presence of magnetic interactions is clear, as they provide the mechanism for angular momentum transport that makes accretion possible. The accretion disk also interacts with radiation produced closer to the black hole. Hard X-rays from the corona strike the disk surface, producing fluorescent emission lines and reflected continua. These reprocessed signals provide another window into the disk's structure and composition. In particular, broadened ion lines have been observed, their profiles shaped by relativistic effects and the motion of gas in the inner disk. Analysis of these lines refines models of the system and offers further evidence of strong gravity at work. In calm detail, the accretion disk is the heart of this high-energy source. Matter drawn from a massive star's wind is reshaped into a flat rotating structure, heated by turbulence and gravity, and radiating with immense power. Its outer zones glow in ultraviolet, its inner regions in X-rays, and its entire structure persists stably over decades. The disk stands as both a physical engine and an observational signature, linking the unseen compact object to the luminous display measured across intergalactic space. The radiation produced by the accretion disk in this system depends strongly on its temperature structure. Each ring of orbiting gas glows according to its own temperature, with the cooler outer regions emitting an optical and ultraviolet light, and the inner regions producing soft X-rays. The result is a smooth spectrum that combines contributions from all radii peaking in the high energy range. This multicolour disk spectrum has become a standard model for describing black hole accretion, and in this particular binary it matches the observed data with impressive accuracy. The shape of the spectrum provides key information about the inner edge of the disk, the rate at which mass is accreted, and the efficiency of energy conversion. At large distances from the black hole, the disk remains relatively cool, with temperatures of only a few thousand degrees Celsius. Here the emission resembles that of hot stars, but it is faint compared to the light of the massive O-type companion. Closer in, as the gas spirals inward and releases more gravitational potential energy, heating intensifies. Temperatures climb to tens of thousands of degrees, producing ultraviolet light that blends with the companion spectrum. In the innermost regions, where orbital speeds approach half the speed of light, the gas is heated to millions of degrees. This zone produces soft X-rays that dominate the system's output and make it visible across intergalactic space. The brightness and colour of the disk are sensitive to the accretion rate. A higher rate increases the density of gas-raising temperatures and shifting the spectrum toward higher energies. Conversely, a lower rate cools the disk and reduces luminosity. In this binary, the supply of gas from the stellar wind remains steady enough that the disk maintains a consistent temperature profile. This steadiness contrasts with the behavior of many other black hole binaries, where fluctuations in mass transfer lead to dramatic shifts in spectral state. The relative calm of this source makes it an important reference point for models of accretion under near-constant conditions. The spectral curve also reveals deviations from a pure thermal profile. Some fraction of the disk's photons interact with the hot corona, above gaining energy through inverse Compton scattering. These upscattered photons form a high-energy tail in the spectrum extending beyond the thermal peak. Observations confirm the presence of this component, though it is weaker here than in systems dominated by hard states. The combination of a strong thermal disk spectrum with a modest high-energy tail is a defining characteristic of this source and reflects its long residence in the soft state. The presence of broadened emission lines provides further evidence of extreme conditions near the black hole. When hard X-rays strike iron atoms in the disk, they produce fluorescent emission at characteristic energies. In this binary, the iron K-alpha line is observed to be broadened and skewed, shaped by gravitational redshift and rapid orbital motion near the innermost stable orbit. These features confirm that the disk extends very close to the black hole, where relativistic effects dominate. By fitting models to these line profiles, astronomers estimate parameters such as inclination inner disk radius and black hole spin. Another aspect of the disk's spectrum is its consistency over time. While small fluctuations occur, the overall shape remains remarkably stable across years of observation. This steadiness implies that the accretion flow remains balanced with inflow and radiation pressure in equilibrium. It also confirms that the system has not undergone the kind of state transitions common in other binaries, where the spectrum shifts between disk-dominated and corona-dominated forms. For researchers, this persistence makes the source a reliable benchmark, simplifying comparisons with theoretical models. The efficiency of energy conversion in the disk is reflected in the luminosity observed on Earth. Even though only a fraction of the stellar wind is captured, the gravitational potential energy released as gas spirals inward produces an output millions of times greater than that of the Sun. This efficiency underscores why accretion is one of the most powerful known processes for generating radiation. In this system, the continuous supply of wind-fed gas ensures that the disk remains luminous, sustaining its glow over decades. Spectral fitting of the disk also constrains the spin of the black hole. The maximum temperature of the disk and the radius of its inner edge depend on how close stable orbits can approach the event horizon. A rapidly spinning black hole allows the disk to extend deeper, increasing both temperature and efficiency. Data from this system suggest that the black hole rotates quickly, though uncertainties remain due to the complexity of modeling the environment. If confirmed, this rapid spin would help explain the high luminosity and efficiency of the disk. Multi-wavelength campaigns combine X-ray, ultraviolet, and optical observations to paint a full picture of the emission. Space-based telescopes capture the high-energy photons, while ground-based observatories measure the cooler output of the outer disk and companion star. By assembling these data across the spectrum, astronomers reconstruct the complete energy distribution. Such studies reveal how the contributions of disk, corona, and star combine to produce the light observed from Earth. They also clarify which features arise from the black hole environment itself, and which are due to the companion or surrounding gas. In calm reflection, the spectrum of this source is both a diagnostic and a demonstration. It shows how gas heated by gravity produces a continuous range of light, with each ring of the disk glowing at its own temperature. It confirms the role of relativity near the horizon, shaping emission lines and broadening their profiles. It reveals the steady nature of the system, with persistent luminosity sustained by wind-fed accretion. Through this spectrum, the hidden compact object becomes visible, not by direct light, but by the radiation released from the matter that encircles it, crossing intergalactic space to reach Earth as a signal of processes unfolding just outside an event horizon. The steady light from this source is not perfectly uniform. When studied with sensitive instruments, the X-ray brightness reveals patterns of variability across a wide range of timescales. On scales of seconds, the light flickers with low-level noise caused by turbulence in the inner disk. On scales of hours, small dips and rises reflect the passage of clumps in the stellar wind across the line of sight. Over days, the orbital cycle imprints its rhythm as the donor star and the compact object circle each other, and our view passes through different regions of absorbing gas. And across years, the overall luminosity remains remarkably steady, making this binary an anchor for long-term monitoring. The 4-day orbit produces predictable changes. As the black hole moves behind the massive star from Earth's perspective, X-rays must pass through more of the stellar atmosphere and wind, leading to temporary reductions in brightness. At other phases, the line of sight intersects denser streams of gas, producing absorption dips in the spectrum. These modulations act as probes of the wind structure, revealing its density, ionization, and clumpiness. By combining X-ray light curves with optical monitoring of the donor star's surface, heating astronomers construct a detailed picture of how the geometry of the orbit shapes the observed emission. Short-term variability originates in the innermost regions of the accretion flow. Turbulence, magnetic reconnection, and fluctuations in the rate of inflowing gas cause the X-ray output to flicker. These variations are subtle in this system compared to more erratic binaries, but they provide valuable clues about the physics of the disk. Analyses using Fourier techniques search for quasi-periodic oscillations, signals that may arise from resonances or orbital motion near the innermost stable orbit. In this case, strong oscillations are absent, consistent with the system's classification as a persistent soft-state source. The dominance of smooth thermal emission leaves little room for sharp timing features, further supporting the interpretation of steady disk accretion. On longer timescales spanning years, the binary has remained luminous without major interruptions. This behavior sets it apart from transient systems in the Milky Way, where long periods of quiescence are punctuated by sudden outbursts. In those cases, disks accumulate matter slowly before releasing it in rapid flares. Here, the continuous wind supply prevents such cycles, keeping the disk fed at all times. The result is persistent emission that has endured across decades of observation, a rare and valuable characteristic. This constancy allows instruments separated by years or even generations to build a continuous record, confirming that the system sustains its balance of inflow and radiation over long timescales. The stability also makes the binary a useful calibration source. Because its brightness and spectrum remain steady, observatories use it to test and adjust instruments. It functions as a natural standard candle, ensuring consistency across missions. Its reliability benefits not only the study of accretion, but also the broader field of X-ray astronomy, where stable sources are rare. Thus, in addition to its intrinsic scientific interest, the system plays a practical role in maintaining the accuracy of observations of the high-energy universe. Despite this steadiness, variability on shorter scales remains of scientific value. Minute fluctuations reveal the chaotic processes of plasma physics near the compact object. Each flicker carries information about the interaction of magnetic fields, turbulence, and radiation pressure at the edge of the gravitational abyss. Sensitive detectors record these signals as random noise, yet careful analysis extracts physical parameters such as coronal temperature, disk viscosity, and magnetic activity. The study of these fluctuations connects the observed light to the microphysics of ionized gas in conditions impossible to reproduce on Earth. Multi-wavelength observations extend the analysis of variability. Optical telescopes detect brightness changes in the heated face of the donor star ultraviolet instruments, capture the cooler regions of the disk, and X-ray satellites monitor the hottest zones. By correlating these signals, astronomers measure how variations propagate through the system. For instance, a burst of X-rays from the inner disk may heat the outer regions, producing a delayed brightening at longer wavelengths. These echoes act as timing experiments, revealing the size and structure of the disk. The delays correspond to light travel times across the system, offering a natural ruler for measuring its dimensions. Variability also arises in the absorption features of the spectrum. As clumps in the stellar wind move across the line of sight, absorption lines deepen or weaken, showing how the gas distribution changes with orbital phase. X-rays ionize much of this wind, creating highly charged ions that absorb at specific energies. The changing depths of these lines trace the density and ionization of the wind, providing evidence of the feedback loop between radiation and mass transfer. The compact object not only feeds on the wind, but also reshapes it through its emission, and variability in absorption features makes this interaction visible. The absence of dramatic state changes combined with subtle variability defines the character of this binary. It is neither quiescent nor unstable, but occupies a middle ground of steady brightness, punctuated by gentle fluctuations. Each dip or flicker serves as a clue pointing to the processes that sustain its luminous balance. Together, these patterns reveal a system that is both stable and dynamic, with a calm exterior that conceals constant motion beneath. In calm reflection, the variability of this source is a record of processes across scales, from turbulence in plasma lasting milliseconds to orbital modulations lasting days to the enduring stability of decades. Each timescale contributes to understanding. The flicker of light traces the chaos of accretion. The orbital dips reveal the wind structure, and the long-term steadiness confirms the persistence of the binary. In the measured glow that reaches Earth, variability and stability coexist, each offering a different layer of insight into the ongoing exchange between a massive star and a hidden black hole. Above the bright surface of the accretion disk lies a region of hot, tenuous plasma known as the corona. Though far less dense than the disk itself, this layer reaches temperatures of hundreds of millions of degrees Celsius, hot enough to alter the spectrum of light that leaves the system. Photons emitted from the disk collide with electrons in the corona gaining energy in a process called inverse Compton scattering. This upscattering produces a tail of harder X-rays superimposed on the softer thermal glow of the disk. Observations of the spectrum show this feature, clearly confirming that the corona plays a consistent role in shaping the emission. The geometry of the corona is uncertain. It may form as a diffuse halo around the inner disk or as smaller regions hovering above it like patches of magnetic activity. Some theories suggest that it is concentrated near the base of weak outflows, where magnetic fields funnel energy upward. Whatever its exact form, its presence is unavoidable, revealed in every high-resolution spectrum as a faint but persistent extension of the emission to higher energies. The relative weakness of the coronal component compared to the disk confirms that the system resides in a soft state dominated by thermal radiation. The origin of the corona is thought to lie in magnetic turbulence. Magnetic fields carried into the disk from the inflowing wind become twisted and amplified by differential rotation. In the inner regions, reconnection events release sudden bursts of energy, heating electrons to extreme temperatures. Some of this energy remains in the disk, but a fraction is deposited into the tenuous plasma above, creating the corona. In this view, the corona is a natural byproduct of the same processes that drive accretion. Its variations in strength and temperature reflect the dynamic interplay of fields and plasma at the very edge of the black hole's influence. Spectral analysis reveals that the coronal electrons reach temperatures of tens to hundreds of millions of degrees, while the optical depth remains low, meaning photons scatter only a few times before escaping. This balance ensures that the corona modifies the spectrum without overwhelming it. In harder states of other binaries, the corona dominates, producing spectra, where the disk is faint and the high-energy tail is strong. Here, the opposite is true. The disk provides most of the luminosity, while the corona adds a smaller secondary component. This contrast makes the system an important example of soft-state accretion, where the corona is present but subordinate. The corona also imprints signatures through reflection. Hard photons scattered by the corona strike the surface of the disk, where they are absorbed and re-emitted as fluorescent lines. The most prominent is the iron K-alpha line, broadened and skewed by relativistic effects near the innermost stable orbit. In this way, the corona indirectly provides a tool for probing the geometry of the disk. The strength and shape of reflection features depend on the corona's position and energy, making them useful diagnostics of its properties. By analysing these features in spectra from observatories such as Chandra and XMM Newton, astronomers refine models of both disk and corona together. Rapid variability is another hallmark of the corona. Because it is diffuse and less massive than the disk, its properties can change on short timescales. Small flares of coronal heating may boost the number of high-energy photons for seconds at a time, producing subtle flickers in the light curve. These events may arise from magnetic reconnection, where field lines snap and realign, releasing energy in bursts. Although the overall emission remains stable, these microvariations add texture, showing that even a steady system contains layers of dynamism beneath its calm exterior. The corona also influences the donor star's wind. Hard X-rays penetrate more deeply into the outflow than softer photons, altering its ionization and structure. Gas exposed to this radiation may lose electrons and change its opacity, affecting how radiation pressure drives the wind. This feedback loop means the corona plays an indirect role in the rate of mass transfer. Absorption lines in the X-ray spectrum sometimes shift with orbital phase, suggesting that coronal activity modifies the wind in real time. Thus, the corona connects the innermost regions of accretion with the wider binary environment. In comparison with other binaries, this system's corona is relatively subdued. Many transient sources in the Milky Way display dramatic shifts in coronal power, flipping between disk-dominated and corona-dominated states. Here the corona never overtakes the disk, providing instead a constant but secondary contribution. This difference underscores the diversity of accretion states among black hole binaries and highlights the value of studying one that remains persistently soft. Its spectra illustrate clearly how a corona modifies but does not control the emission, offering a simpler case for modelling. From the perspective of high-energy astrophysics, the corona of this binary demonstrates how accretion produces multiple layers of radiation. The disk shines with thermal light, the corona adds a harder extension, and their interaction yields reflection features that encode the dynamics of the inner flow. Together they create a spectrum rich in information, even though the compact object itself remains unseen. Each photon that escapes carries a trace of both the disk and the corona, evidence of matter and energy interacting under conditions of extreme gravity. In calm description, the corona completes the portrait of the system. It is a veil of hot plasma above the disk, scattering photons into higher energies, adding variability and linking the innermost regions to the surrounding wind. Though less dominant than the disk, it is essential to the full picture of accretion. By studying its spectrum variability and reflections, astronomers gain insight into plasma physics and magnetic activity near a black hole. The corona is therefore not just an accessory, but a key layer in the luminous structure that defines this high-mass X-ray binary. In many accreting black hole binaries, matter is not only drawn inward, but also expelled outward in the form of jets or winds. These flows carry energy and angular momentum away from the system, linking the inner accretion processes to the larger galactic environment. In this particular binary, no strong jet has been confirmed, yet careful observation reveals evidence for weaker outflows. The absence of bright radio emission, which would indicate powerful relativistic jets, is consistent with the source's steady soft state. Theory and observation both suggest that jets are suppressed when the disk dominates the emission. Even so, the possibility of faint or intermittent jets remains detectable only through subtle signatures. more secure evidence exists for disk-driven winds. High-resolution X-ray spectra display absorption features from highly ionized iron and other elements shifted toward lower energies in a way that indicates outflowing motion. These lines reveal gas escaping the system at thousands of kilometers per second. Such winds are distinct from the stellar wind of the companion star arising instead from the surface of the accretion disk itself. They are launched by a combination of radiation pressure and magnetic forces, creating streams of gas that flow outward, even as most of the material spirals inward. The presence of disk winds highlights the balance between inflow and outflow. Only a fraction of the captured stellar wind reaches the black hole. Some of it is expelled again by the disk, reducing the efficiency of accretion. This feedback regulates the luminosity, preventing runaway growth. At the same time, the winds carry energy and material into the surrounding interstellar medium, contributing to the ecology of the Large Magellanic Cloud. Though the effect of one system is small on galactic scales, the combined influence of many such binaries shapes the heating, ionization, and turbulence of star-forming regions. Interactions between outflows and the companion star's wind add complexity. Where the two flows meet, shock fronts form, compressing and heating the gas. These shocks may produce additional spectral features or alter the density distribution around the binary. In some phases, the line of sight passes through regions where disk winds and stellar winds overlap, creating variable absorption signatures. This interplay demonstrates how the system is not merely a source of radiation, but also a dynamic engine shaping its local environment. The physics behind jet formation remains an active area of research. In many black hole binaries, jets are thought to be powered by magnetic fields anchored in the disk, or by the rotation of the black hole itself. If the compact object spins rapidly, its rotational energy can be tapped through magnetic interactions, launching collimated outflows at relativistic speeds. For this binary evidence points to a spinning black hole, yet the lack of strong jets implies conditions that suppress this mechanism. Perhaps the dense luminous disk of the soft state prevents magnetic fields from building up to the required strength. Alternatively, only faint jets may exist, producing radio emission too weak to dominate the spectrum. Even if powerful jets are absent, the detection of winds is significant. Observations show that these outflows vary with orbital phase, suggesting a structured and possibly clumpy origin. Their speeds of thousands of kilometers per second make them important carriers of angular momentum, altering the balance of the accretion process. Over long timescales, such winds can influence the orbital evolution of the binary by removing mass and momentum from the system. In this way, the outflows link small-scale accretion physics to the large-scale fate of the binary. Comparisons with other systems confirm that disk winds are a common feature of luminous accretion. In the Milky Way, similar absorption lines have been observed in soft-state binaries, while hard-state binaries show stronger jets. This contrast supports the idea of a state-dependent trade-off between winds and jets. In one regime, outflows take the form of disk winds. In the other, they emerge as relativistic jets. The binary in the Large Magellanic Cloud fits this pattern, standing as a stable example of the wind-dominated mode. These winds also affect how the system evolves chemically. Gas expelled into the interstellar medium carries heavy elements processed in the companion star. Over time, this enriches the surrounding region, contributing to the chemical evolution of the galaxy. Although a single binary has only a modest impact, the cumulative effect of many such systems may shape the metallicity of future generations of stars. The contribution of this source is therefore part of a broader cycle, linking black hole accretion to galactic evolution. From an observational perspective, the search for outflows remains ongoing. Radio telescopes continue to monitor for faint jet signatures, while X-ray observatories refine measurements of disk winds. Each new detection adds detail to the picture, clarifying the role of outflows in the overall energy budget. Even the absence of strong jets provides information confirming theoretical predictions about the suppression of jets in the soft state. Thus, the system continues to serve as a touchstone for understanding how inflow and outflow coexist in black hole binaries. In calm summary, the binary does not simply draw material inward, but also releases part of it outward. Gas spirals toward the black hole, radiates its energy and vanishes, yet other gas is driven away in disk winds carrying matter and momentum back into space. Whether faint jets accompany these winds remains uncertain, but the evidence for outflows is clear. These processes demonstrate the balance of accretion, where not all captured matter is consumed, but some is returned to the galaxy. In this balance, the system links the hidden depths of a black hole to the wider environment of the Large Magellanic Cloud. The innermost regions of the accretion flow are shaped not by Newtonian gravity, but by the laws of general relativity. Here the curvature of space-time dictates the motion of matter and the paths of light, producing effects that cannot be explained with classical mechanics. Gas in the inner disk orbits at speeds approaching half the speed of light, and the photons it emits are altered by the gravitational well they must escape. Gravitational redshift shifts their energies downward, while light bending curves their trajectories so that emission from the far side of the disk can still reach Earth. These relativistic effects combine to produce broadened and asymmetric spectral lines, signatures that have been measured in the spectrum of this system and interpreted as evidence of extreme conditions near the event horizon. One of the most critical concepts is the innermost stable circular orbit. This is the smallest radius at which matter can maintain a steady orbit before plunging directly into the black hole. For a non-spinning black hole, this orbit lies at 3 times the radius of the event horizon. For a rapidly spinning black hole, it moves closer, allowing the disk to extend deeper into the gravitational well. Observations of the thermal spectrum here suggest that the disk does indeed reach very close to the horizon, implying that the black hole is rotating rapidly. The high luminosity and efficiency of the system support this interpretation, as only a spinning black hole can convert such a large fraction of mass into radiation. Another relativistic effect that may operate is frame dragging. In this phenomenon, the rotation of the black hole twists space-time around it, forcing matter and light to follow curved paths. Gas in the inner disk experiences this drag, its orbit slightly altered by the rotation of space-time itself. While direct measurement of frame dragging is difficult, theoretical models that include spin reproduce the observed spectrum better than those that do not. The broadening of iron lines and the high temperatures of the disk are both consistent with rapid spin and frame dragging effects. Time dilation also plays a role. To a distant observer, processes near the event horizon appear to slow, with photons emitted at longer and longer wavelengths. Matter spiraling inward seems to linger near the horizon, fading away rather than disappearing abruptly. In reality, the gas crosses the horizon in finite time, but its signal is stretched and dimmed until it is lost. The light that does escape carries evidence of this slowing, embedded in the energy shifts and timing behavior of the X-rays that reach Earth. The high velocities in the inner disk add to these effects. Gas moves at a significant fraction of the speed of light, producing Doppler shifts that broaden emission lines. On one side of the disk, motion toward Earth, blue shifts the light, while on the opposite side, motion away red shifts it. Combined with gravitational redshift and light bending, the result is a complex line profile with extended wings. These profiles are invaluable for probing the inner geometry. In this system, the shape of the iron K-alpha line matches predictions for a disk, orbiting deep within a relativistic gravitational well, further confirming the presence of a black hole. The efficiency of energy release depends on how close matter can orbit before plunging inward. For a non-spinning black hole, about 6% of the mass energy of infalling matter is radiated away. For a maximally spinning black hole, efficiency can rise to more than 40%. Estimates for this binary place it well above the non-spinning value, supporting the conclusion of significant spin. Such efficiency explains the persistent brightness even when only a small portion of the stellar wind is captured. Relativistic effects also alter the appearance of the disk itself. Light bending makes the disk seem larger than it truly is, as emission from its far side curves into view. This creates the illusion of a nearly complete ring of light, even though part of the disk would otherwise be hidden. The inner regions, brightest and hottest, dominate the spectrum, their photons most strongly affected by gravity. What reaches Earth is therefore not a simple thermal glow, but a spectrum imprinted with the signatures of curved space-time. Comparisons with other systems reinforce these conclusions. Inactive galactic nuclei, where supermassive black holes accrete matter on vastly larger scales, the same relativistic effects are seen. The difference lies in the timescales processes that take hours in a stellar mass binary unfold over years in a galaxy core. By studying a nearby stellar mass system, astronomers gain insight into physics that applies universally from binaries in the local group to quasars billions of light-years away. The binary in the Large Magellanic Cloud thus provides a manageable and persistent laboratory for testing general relativity under conditions of strong gravity. The persistence of the soft state also aids in isolating relativistic features. In transients, variability can obscure the signatures, but here the steady disk allows spectral features to be observed clearly. The broad iron line and the high disk temperature stand out against the smooth continuum, offering consistent evidence over decades of observation. Each new instrument confirms the same picture, a black hole spinning rapidly, accreting steadily, and shaping its radiation through the curvature of space-time. In calm description, the innermost regions of this binary demonstrate the reach of relativity. Matter orbits at extreme speeds. Light is bent and redshifted, time itself is distorted, and energy is released with extraordinary efficiency. The compact object remains unseen, yet its presence is written into every photon that escapes. Through careful observation of spectra and timing, astronomers trace the invisible geometry of spacetime, confirming that even in a galaxy beyond our own, the predictions of general relativity hold true in the depth of a black hole's gravity. At the innermost edge of the accretion flow lies the event horizon, the defining feature of a black hole. For the compact object in this binary, the horizon is only a few dozen kilometers in radius, yet it governs everything that happens in the surrounding region. Beyond this limit, no signal can return, not light, not matter, not information. Observers can never look inside. Instead, they must study the behavior of gas and light just outside the boundary. Infalling material releases its remaining energy as radiation before crossing the horizon, then disappears from the observable universe. The glow recorded from Earth is therefore the final expression of matter's journey before silence. The event horizon produces no light of its own. Its existence is inferred from what is absent. In systems with neutron stars in falling matter, strikes a hard surface producing bursts of X-rays and thermonuclear flashes. Nothing of the sort has ever been seen from this source. Its emission is consistent with accretion onto an object that lacks a surface one where matter simply vanishes once it crosses a threshold. This absence, together with measurements of mass far above the neutron star limit, leaves the black hole interpretation as the only consistent explanation. Photons emitted just outside the horizon are profoundly altered by gravity. Their energies are reduced by gravitational redshift, and their paths are bent by the curvature of space-time. Some skim close to the horizon and circle the black hole before escaping, while others fall inward and are lost. These effects sculpt the radiation that does reach Earth, producing broadened emission lines and smoothed spectral features. The iron K-alpha line in particular shows the unmistakable skew and extension expected from light emitted in the grip of strong gravity. Even though the horizon itself is invisible, its presence is written into these distortions. From a distant perspective, matter approaching the horizon seems to slow its light dimming and redshifting until it fades away. This appearance is an effect of time dilation caused by the immense gravity. In the local frame of the infalling gas, however, the plunge across the horizon occurs in finite time. This duality highlights the difference between local experience and distant observation, a distinction predicted by general relativity, and supported by the behavior of light curves and spectra from this system. The event horizon also sets the scale for efficiency. As matter falls deeper into the potential well, more of its mass energy is converted to radiation before the final plunge. Once across the horizon, no further emission occurs. This makes the region immediately outside the boundary the most luminous part of the system. Photons emerging from here carry the last available information about the gas encoded in their energies and directions. They travel across 160,000 light-years to reach Earth, bearing silent witness to the processes unfolding just beyond the point of no return. The absence of surface phenomena, the extreme luminosity, and the relativistic line profiles together confirm the reality of the event horizon. Alternative models involving exotic compact objects with surfaces or partial horizons fail to reproduce the observations. Only a black hole with its defining boundary explains the data. In this way, the system stands as one of the clearest extragalactic demonstrations of event horizon physics. It shows that black holes are not abstract predictions but observable entities whose properties can be inferred through careful study of the light escaping their grasp. The horizon also marks the final boundary of knowledge, everything that can be observed: the disk, the corona, the winds, the relativistic distortions occurs outside. Everything inside is hidden unreachable by any instrument. This limit defines the scope of astrophysics, setting the line between what can be measured and what must remain beyond observation. The black hole is therefore not only a physical object, but also a marker of the edges of science. Its event horizon a natural division between knowable and unknowable. Even unseen, the horizon influences its surroundings. Its gravity dictates the structure of the disk, the speed of orbits, the efficiency of radiation. Its existence explains the silence where other compact objects would roar. Its boundary shapes the light that bends and stretches as it escapes. Each of these effects builds the case for its reality, and together they paint a consistent picture of a true black hole accreting matter in a neighbouring galaxy. In calm description, the event horizon is not a surface that can be touched or crossed in any ordinary sense, but a limit where space-time curvature becomes absolute. For the massive star, for the disk, and for the outflows, it represents the end point of interaction. For astronomers, it defines the edge of vision. The steady glow recorded from Earth is the outward trace of matter spiralling to this boundary and then vanishing, leaving no further signal. In this glow lies the signature of the horizon, the final confirmation that the system contains a black hole and nothing less. The influence of this binary extends beyond the immediate pair and into the surrounding environment of the Large Magellanic Cloud. X-rays released near the black hole radiate outward, striking gas clouds and altering their physical state. Neutral atoms are stripped of electrons, molecules are dissociated, and the balance between heating and cooling in the interstellar medium shifts. The donor star also contributes strong ultraviolet light, but the X-rays penetrate farther ionizing regions, otherwise shielded from starlight. The result is a bubble of ionized gas around the system, a structure that reflects the continuous flow of energy outward. The winds and radiation interact in complex ways. X-rays ionize gas in the donor star's outflow, reducing its opacity and changing the efficiency of radiation driving. Clumps of wind may be eroded by this radiation, while diffuse gas becomes more transparent. The process alters the very supply of material that sustains accretion, creating a feedback loop. The black hole feeds on the wind, yet its emission reshapes the flow, smoothing some regions while breaking up others. This constant interplay stabilizes the system, ensuring a balance between inflow and feedback that maintains its persistent state. On larger scales, the cumulative effect of systems like this contributes to the ecology of their host galaxies. In star-forming regions, high-mass X-ray binaries inject heat and ionization into molecular clouds, influencing the conditions under which new stars form. Though a single binary's impact is modest, many such sources together create a background of high-energy radiation. In the Large Magellanic Cloud, where young clusters abound, this contribution is significant. The presence of persistent sources like this one ensures that the galaxy's interstellar medium remains stirred, heated, and chemically altered by the products of accretion. Mechanical feedback accompanies radiative feedback. Disk-driven winds, though weaker than the donor's stellar wind, carry angular momentum and mass away from the system. Over time, these outflows inject energy into the surrounding interstellar gas, driving turbulence and carving small-scale cavities. Surveys of the region show structures consistent with such processes, evidence that compact binaries contribute to the shaping of their environment. Though less dramatic than supernova explosions, the continuous output from X-ray binaries represents a steady and lasting influence. The evolutionary path of the system is also tied to its environment. The donor star will live only a few million years before exhausting its nuclear fuel. As it evolves into a supergiant, it may fill its Roche lobe and begin transferring matter directly rather than through winds. In that phase, accretion would intensify, the luminosity could rise, and the spectrum might change state. Eventually, the star will undergo core collapse, likely producing a supernova and leaving behind another compact remnant. If the binary survives the explosion without disruption, the result could be a pair of compact objects, two black holes, or a black hole and a neutron star bound in orbit. Such a pair would continue to spiral closer through the emission of gravitational waves, eventually merging in a burst detectable across the universe. This fate lies far in the future, but it is part of the natural sequence of evolution for massive binaries. In the present, the system exemplifies a steady phase, but its long-term trajectory links it to the broader context of compact object mergers and the growing field of gravitational wave astronomy. The importance of this source is therefore both immediate and long-term. Immediately, it provides a persistent laboratory for studying accretion winds and feedback under conditions of strong gravity. Over the long term, it represents one stage in the life cycle of massive stars and their remnants, a stage that may eventually produce phenomena detectable across cosmic distances. By observing it now, astronomers capture a stable configuration that will not last, but whose lessons apply across both stellar and galactic evolution. Comparisons with other binaries reinforce these insights. Some systems in the Milky Way show burst jets or transients, while this one remains steady. Together they illustrate the diversity of outcomes in high-mass binaries. The steady glow of this extragalactic system shows one path where wind-fed accretion maintains a persistent disk and corona moderated by feedback and stabilized by orbital balance. Its behavior provides a reference against which the more erratic systems can be compared, anchoring the field with a clear and consistent example. The study of this binary also links local physics to cosmic principles, the processes that govern its emission wind capture disk accretion. Relativistic heating feedback into the environment are the same processes that occur on vastly larger scales in active galactic nuclei. By understanding a stellar mass black hole in a nearby galaxy, astronomers gain a clearer view of quasars and radio galaxies billions of light-years away. The scale differs, but the physics is universal. In this sense, the system is not just a local object, but a representative of a class that spans the cosmos. In calm description, the binary is both a particular source and a general model. It demonstrates how a massive star and a black hole can coexist in stable orbit, how matter flows from one to the other, how radiation escapes and alters its surroundings, and how such systems fit into the grand cycle of stellar and galactic evolution. Its light has travelled 160,000 years to reach Earth, carrying within it the story of accretion, feedback, and persistence. In that light, the presence of a black hole becomes not only inferred, but observed, its influence extending far beyond the horizon to the interstellar medium of its host galaxy.